Hello, I'm doing problem 2.3.10. The original equation is tx prime plus 2x plus t squared. Tx prime is equal to 2x plus t squared. And we collect the x terms together and divide by t so that we get x prime as the leading term. Notice that we're assuming that t is not equal to 0 to do this. We might have to deal with that later. All right, we wanted an integrating factor, something whose derivative will give us this minus 2 over t. And so we get that p is minus 2 log t. If we take the exponential of that, that's e to the whole product minus 2 times log t. And by the rules of exponentials, that's e to the one of the items in the product raised to the power of the other one. So that's e to the log t raised to the power minus 2, which is 1 over t squared. Let's see what that gives us. If we take the derivative of 1 over t squared x, we get the derivative falling on x, so that's 1 over t squared x prime. And then when the derivative falls on 1 over t squared, we get minus 2 over t cubed x. And so that's 1 over t squared times x prime minus 2 over tx, and that's t. So that's 1 over t squared times t, which is 1 over t. So this is something we can anti-differentiate because we have a derivative on the left-hand side, and on the right-hand side we have 1 over t, which we can anti-differentiate. So let's do that next and we'll get a solution. We round up with 1 over t squared x, the whole thing differentiated equal to 1 over t. We anti-differentiate both sides. And again, I'm assuming here that t is positive, so that integrating 1 over t gives log t. If t is negative, then it's log of the absolute value of t. And one way or the other, if I solve for x by multiplying by t squared, I get x is t squared times the log of the absolute value of t plus c, whatever this constant is, times t squared. As t goes to infinity, t squared log t grows faster than t squared. And so this goes to infinity even if c is negative. Incidentally, if x has a value at 0, that value has to be 0, because if you look at this equation, x at 0 has to be equal to 0. But it's not clear to us, even if x at 0 is 0, whether there is a solution to this equation or not. Here is 2.3.14. The equation was x prime plus 2tx is equal to 3t. We'd like to use an integrating factor to take care of this 2t part, and then solve this with x of 0 equal to 4 as our initial condition. So the integrating factor is supposed to have derivative 2t, and so that is p is equal to t squared. Let's check. If we take e to the t squared times x, differentiate that product, we get e to the t squared times the derivative falling on x. And then when we differentiate the e to the t squared, we get the e to the t squared again times 2t, and of course the x was there. And so we indeed have x squared plus 2tx multiplying e to the t squared, and so we get e to the t squared times 3t. We anti-differentiate both sides, we get e to the t squared x is equal to 3/2 e to the t squared, and then a constant of integration. Solving for x by multiplying by e to the minus t squared on both sides, we get x is equal to 3/2 plus c e to the minus t squared. You can check that if I put x equal to 3/2 in here, the derivative is 0, and then 3/2 times 2t is 3t, so that's a particular solution. And you can check that if I put e to the negative t squared here, then that gives, on the left-hand side, that gives 0. So that's the homogeneous solution. And so let's solve for the constant. 4 is x at 0. If I put in 0 for t, I get e to the 0, which is 1. So that's 3/2 plus c. and so x is 3 halves plus 5 halves e to the negative t squared.